So let me just, so this second point will really come in the second tomorrow, so we'll sort of really go back to these basics, because the whole motivation for this was this first issue about how to make sense of entanglement. So I've got, just like the previous speaker, a few kind of quotes to start with, and I think there's no better person in the field than Bell himself. So this is from his paper, Free Variables and Local Causality, which I got from his book, The Speakable and Unspeakable in Quantum Mechanics book. So he says, to start with, quantum mechanics is not locally causal and cannot be embedded in a locally causal theory. So that's, that's essentially the message from the Bell theorem, that the Bell inequalities, which are satisfied if you have a locally causal variable theory, are violated, and therefore quantum mechanics is not locally causal. Now, he then goes on to sort of emphasize the point that conclusion, the conclusion of this sentence here, depends on treating certain experimental parameters, like the orientation of polarization filters or orientation of Stern-Gerlach apparati, as free variables. In other words, you derive the Bell inequalities for hidden variable models by kind of assuming, well, the hidden variables, they don't know exactly what measurement you're going to do, but they're kind of prepared for any particular choice of Stern-Gerlach orientation you may choose to do. Okay, so the whole derivation of the inequalities treats these experimental parameters as free variables. Now, Bell points out in this paper that, and he's quoting from, I think, a paper by Shimoni and others, about sort of the metaphysics of this issue about free variables. So he says, in this matter of causality, it's sort of an inconvenience that the real world, I mean, I think this paragraph is slightly tongue-in-cheek, but as far as I can understand, but he's responding to a paper, as I say, by Shimoni, which raises a kind of metaphysical question about what does free variable really mean. So he says, in this matter of causality, it's a great inconvenience that the real world is given to us once only. We cannot actually know what would have happened if something such as one of these experimental parameters had been different, because we can't repeat an experiment changing just one variable. At the very least, if you do the experiment changing a variable, it'll be at a different time, so the hands of the clock will have moved, or the moons of Jupiter will have moved, or something. So this notion, what does it mean to think of, say, an experimental parameter as a free variable, is metaphysically kind of loaded with difficulty. But in a sense, Bell then goes on to say, frankly, I'm not, this is my interpretation of trying to read this, I think he's kind of saying, well, this is kind of interesting from a philosophical point of view, but, I'm a physicist, and I don't really care about these philosophical issues. As far as I'm aware, I'm dealing with physical theories, and physical theories either have free variables or they don't. So, he says physical theories are more amenable, if you like, than the real world in this respect. We can calculate the consequences of changing the free elements in a theory. They may only be initial conditions, they may be certain parameters and so on, but we can explore the causal structure of the theory. So his claim is that the Bell theorem, the proof of the Bell theorem, is really an analysis of certain kinds of physical theory, and I've sort of emphasised that point because it's something I want to come back to, because for me this issue is it's an interesting one. The fact that in reality, we can't actually keep everything fixed and just change the parameter of some experiment, because things in the external world will have changed. But the question is, can one try to address this issue within a framework that Bell himself would have felt comfortable with? In the sense, are there certain kinds of physical theory for which these types of Shimoni-type metaphysical questions are brought to the fore? Okay, now just the last bit of the quote. He says, contemporary quantum theory, as it is practiced, do have free external variables. So that's fine as far as contemporary quantum theory. But what I want to address here is if you like, a different kind of physical theory. Now, at this stage, I don't want you to even think about whether or not this type of physical theory is something in which quantum mechanics can be embedded. I mean, I will make the claim later on that perhaps it can, but at this stage, let's not go down that road of whether this has got anything to do with quantum theory or not, but just try to think about the consequences of the Bell theorem with respect to this kind of physical theory. Now, the kind of physical theory I'm talking about is the famous Lorentz, the meteorologist Lorentz attractor. So it's a chaotic model. Now, I should at this point say that many people have, or at least a number of people anyway, have addressed the issue of whether chaotic dynamics can in some sense be brought to bear on the Bell problem. And the general, and for example, Penrose in one of his early books discusses it, David Deutsch discusses it, I'm sure a number of other people do. And their view is no, this is irrelevant as far as the Bell theorem is concerned. The Bell theorem addresses wholly different issues than have got to do with chaos. However, when people of that type, Penrose, Deutsch and others, talk about chaos theory, they're basically talking actually just about the differential equations. So this flow is described by three non-linear coupled ordinary differential equations. And when people talk about chaos theory, they refer to just those three differential equations as the defining system. However, when I was brought up as doing maths at university, I was told, you were marked down if you tried to solve an equation without take a differential equation without also considering the boundary conditions or the initial conditions. So the system was not only the differential equation, it was the boundary or initial conditions as well that define the system. And what I want to do is to consider a system which is governed by those differential equations, but a system which, let's say, is initialized or lies on the invariant set, or in this case the attractor set, of those differential equations. Now, chaos is often used to just denote kind of some sort of unpredictability, and I want to slightly get away from that perspective, because the unpredictability is not something I consider to be of primary importance. And I'm going to actually use a phrase that Lorentz himself used in his Lorentz himself used in the title of his paper, in the 63 paper on chaos. He didn't call it chaos. The word chaos only came about in the 70s when people rediscovered Lorentz's work. He called it deterministic non-periodic flow. And I want to call the system I'm talking about is on attractor deterministic non-periodic flow. So I'm talking about flow that is on this sort of invariant set of the system. Just as an aside, this is something I have been unable to actually ascertain rigorously whether this is true or not. But I've contacted a number of my colleagues of a more mathematical nature than I am to ask whether they think it's true, and everybody says they think it's true, but nobody seems to come up with a definitive proof. It's known, for example, that the Mandelbrot set, which is that sort of quadratic mapping of the Argand plane, produces a fractal. That's known to be, so membership of the Mandelbrot set is known to be recursively undecidable in general. And my belief is the same is true also of these dynamical system attractors. So, for example, if you wanted to prove rigorously that a point P, sort of at random on the plane, lies on the attractor, then one condition, for example, would be that the trajectories, the orbits under the set of differential equations from P, would have to repeatedly pass through an arbitrarily small neighbourhood of P. And that's clearly something that, it's going to be, let's say, difficult to do in finite time recursively. So I think this is true, that this